in statics and mechanics of materials, we learn how to draw shear force and bending moment diagrams. Most of the time, we cut the beam, write the equilibrium equations, and calculate the internal forces. But from that point on, those internal forces stop feeling like something physical and start feeling like something we are just supposed to calculate. And once that happens, many of you start getting lost in the signs like upward or downward, clockwise or counterclockwise. And when the loading becomes more complicated, the whole thing starts to feel overwhelming. So in this video, we are going to clear that up. I am not going to throw equations at you. We will look at the physics of how internal forces appear and how they get passed along. Once that starts to click, a lot of the confusion clears on its own, and shear force and bending moment diagrams stop feeling like graphs you have to wrestle with. They start feeling like pictures you can almost sketch at a glance. Let's begin. Here we have a beam with a point load and a point moment. If this beam is at rest, then the support reactions must exist. Otherwise, equilibrium would be impossible. Let's split the beam into small elements. What happens between those elements? Let's look at the first one. A point load P is acting on this element. For force equilibrium, this element has to receive an additional force from somewhere. And the only place that force can come from is the face on the right. Everywhere else is just empty space. So the second element applies a force to the right face of the first element. Let's call them V1 and M1. That puts the first element in equilibrium. But hold on. If there is an action, there has to be a reaction. That's Newton's third law. So an equal and opposite V1 and M1 appear on the second element as the reaction. That leaves the second element looking out of equilibrium. So let's look at that one next. Exactly the same thing happens. To stay in equilibrium, it has to receive the force and moment it needs from the third element. Let's call them V2 and M2. Now the second element is in equilibrium as well. And that reaction gets passed on to the third element. The third element works the same way. Action, equilibrium, reaction, and the process repeats, like falling dominoes. Suppose that, somewhere in this process, one of these tiny elements encounters an additional load, nothing really changes. That element still reaches equilibrium and passes the effect along to the next one. The same applies if it encounters a support reaction. And in the end, the last element is balanced by the pin support reaction. Even if we split the beam into just two pieces instead of many, it is still just action and reaction. The mechanism at the section is exactly the same. The force and moment that arise through the interaction of two elements across one section, those are what we call internal forces or section forces. That includes axial force, shear force, and bending moment. You might be thinking this. If the magnitudes are equal and the directions are opposite, then once we put the elements back together, wouldn't they just cancel out? No. And this is the part that really matters. These are an action-reaction pair. Each force and moment acts on a different element, so they cannot be physically combined into one. So even after you put the elements back together, they do not disappear. They still exist inside the material. And here's the key point. An internal force represents a physical state. To define that state properly, you need all three of these together. One boundary surface, two elements, and an action-reaction relationship. The problem starts when we try to express that physical state with a number. If someone simply says there is a shear force of 3 newtons at that section, the listener can get confused. Because that statement alone doesn't tell you which physical state they mean. That's why we need a sign convention. Which state we decide to call positive is up to us. Nature does not choose it for us. A sign convention is simply an agreement. There is no absolute rule. It lets us represent the physical state at a section with a number. That said, for horizontal beam-like members, there is a widely used convention. So from this point on, we'll treat this internal force state as positive and the opposite state as negative. For convenience, the sign convention is often drawn like this. But in that picture, you no longer really see one boundary surface, two elements, and an action-reaction pair. And that can make it easier to lose sight of what an internal force really is. So personally, I prefer the first way of drawing it. Anyway, under this sign convention, if someone says there is a shear force of -3 newtons, then this is the state they mean. And if someone says there is a bending moment of -5 newton meters, then this is the state they mean. So the sign of an internal force does not, by itself, mean a direction. It means a physical state, defined by the sign convention we chose in advance. So that is the basic idea behind the sign convention. And even so, this is still exactly where a lot of people get confused when they solve actual problems. Why is that? Usually, it's because textbooks introduce this idea inside the equilibrium equations. So here, let's briefly look at the grammar of that calculation. We're not trying to do the full calculation. We just want to see why the signs can start to feel confusing. Suppose we have a beam in equilibrium, and we make an imaginary cut. We do not yet know the physical state of the internal force at that cut. So for the moment, let's assume a positive internal force state. Each cut piece has to satisfy equilibrium on its own. So for each piece, the sum of forces and the sum of moments must be 0. Let's write those equations. And here's the point to notice. Those equilibrium equations are written in the global coordinate system. So inside the equations, the signs simply represent directions relative to the coordinate axes. But the sign of the internal force we get after solving the equations is not a direction in the global coordinate system. It is the physical state of the internal force under the sign convention. The same is true on the other side. And if I remove all the visual cues and leave only the equations, yes, it starts to look pretty confusing. That is where the confusion begins. Because it feels as if the meaning of the sign keeps changing. There is one clean way to remove that confusion. Set the global coordinate system aside for a moment. Instead, take the positive internal force direction at the section itself and use that as a new local coordinate system when you write the equilibrium equations. Then the direction in the equation lines up directly with the physical state. And on the other side, if we do the same thing, and again use the positive internal force state as the new local coordinates, we get this. Again, the direction lines up directly with the physical state. And yes, the numerical result is exactly the same. This local coordinate approach is actually pretty useful. But even that still belongs to the calculation framework built around equilibrium equations. Don't worry. In this video, we're not going to focus on internal forces mainly through that calculation framework. What we want to see is how internal forces are created and how they get transmitted. That is the physical core of the whole thing. Let's go back to the beam. With the sign convention in place, let's look at how those internal forces change along a simple cantilever beam. Each internal force gets plotted on the shear force and bending moment diagrams according to that sign convention. Since no additional load acts on each element, the shear force created by the interaction stays constant at every section. But the moment gets larger from one element to the next, because each element picks up an additional amount of moment equal to v times delta x. So the moment required for equilibrium keeps growing. and the last element is balanced by the support reaction at the fixed end. If we now imagine these elements becoming infinitely short, then we can know the shear force and bending moment at every section. Let's look at a slightly different example. The same cantilever beam now has both a point load and a point moment acting on it. The principle is the same. Everything still comes down to equilibrium and transmission. The first element receives the point moment. It receives the balancing moment it needs for equilibrium and passes that along through the reaction. That transmission continues, and then it encounters a clockwise point moment. At that element, it receives the moment required for equilibrium from the neighboring element and transmits the reaction onward. As it passes that clockwise point moment, the bending moment makes a positive jump by that amount. And again, positive here does not mean clockwise or counterclockwise as a direction. It means the physical state of the bending moment under the sign convention. After that, the elements do not encounter any more external loads, so they just keep repeating the same equilibrium and transmission process with no special change. Then eventually, we meet the point load. For the element to stay in equilibrium, it now needs an upward force. And because of that point load, the balancing moment becomes a little smaller. As we pass the point load, P, the shear force jumps to the negative side. And again, that negative sign does not mean upward or downward as a direction. It means the physical state of the shear force under the sign convention. After that, equilibrium and transmission continue again. The shear force stays constant, and the bending moment keeps getting smaller. So the full diagrams across the beam look like this. But are we really supposed to split the beam into tiny pieces every single time and draw the diagrams that way? No. This was only to show you that equilibrium and transmission are the real core of the mechanism. What really matters is how much the internal forces change during this transmission process. To see that, let's take a distributed load as an example. So what happens when a distributed load acts on an element? For equilibrium, the element receives a force and moment from the next element and passes them along as the reaction. What I want to know is this: how much do the force and moment change from one section to the next? Let's write the equilibrium equations for a moment and take a look. The result is actually very intuitive. Each change is exactly the amount needed to cancel the force and moment imbalance created by the distributed load. If we take the element to be very small, then the delta x squared term becomes small enough to ignore. And the relationship becomes even simpler. Sometimes this is written in differential form. Sometimes it is written in integral form. The meaning is the same. But to keep the intuition clear, I'm going to stick with the original form. The first equation tells us that the change in shear force is equal to the area of the distributed load. At each dx, the shear force decreases by the area of that distributed load. If the distributed load changes, then that area changes too, and the shape of the shear force diagram changes with it. The second equation works the same way. The change in bending moment is equal to the area under the shear force. At each dx, the bending moment changes by the area under the shear force. And again, if the shear force changes, then the area changes, and the shape of the bending moment diagram changes as well. Of course, you can also read all of this in terms of slope. With that in mind, let's draw the diagrams directly. If we have a cantilever beam like this, then the distributed load is constant over the whole length. So the shear force has to change at a constant rate. In other words, the decrease at each delta x must be constant. Let's plot that on the shear force diagram. That gives us a straight line. the total accumulated decrease is equal to the full area of the distributed load, so the shear force at the last element will be minus 12 newtons, and that balances the support reaction. For the bending moment diagram, as delta x increases, the shear force becomes more and more negative, so the amount of decrease keeps growing. That means the bending moment diagram will be a curve bending downward like this. The total accumulated decrease is equal to the full area of the shear force diagram, so the bending moment at the last element will be minus 24 Newton meters. And that balances the fixed end moment at the last element. For another example, consider an element cut at a section extremely close to x equals 0. This element receives the support reaction as an external force, and it has to be balanced by internal forces. So that determines the starting value of the shear force. After that, since the distributed load gradually decreases, the shear force also decreases like this as delta x increases. The bending moment works the same way. Its starting value is determined by equilibrium. And because the area under the shear force gets smaller as delta x increases, the bending moment diagram will look like this. At the end point, the slope must be 0, and the value itself must also be 0, because this is the free end. Next, take an example with no distributed load at all. The support reactions look like this. The starting value of the shear force is positive 2.5 newtons. Since the distributed load is 0, the shear force does not change. So the shear force is just a horizontal line. What happens when the element encounters a point load of 4 newtons? To stay in equilibrium, it has to receive an additional upward force of 4 newtons. In the equilibrium and transmission process, that means the shear force makes a negative jump of 4 newtons. After that, no more loads act on the beam, so the shear force stays constant again. For the bending moment diagram, based on the area under the shear force, it increases steadily and then decreases steadily. And if the element encounters a point moment, then by the same equilibrium and transmission mechanism, the bending moment makes a positive jump of 2 Newton meters. After that, it decreases steadily again according to the area under the shear force. Simple, right? This loading looks a bit more complicated. But now, we can draw it pretty easily. First, we draw the shear force diagram using the relationship between distributed load and change in shear force, together with the equilibrium and transmission process at each point load. Then we use that shear force diagram to draw the bending moment diagram. Where the shear force jumps, the change in bending moment also changes abruptly. So you can think of that as a discontinuous change in the slope of the bending moment diagram. In the remaining region, the shear force becomes negative, so the bending moment decreases. And once we also account for the jump at the point moment, the bending moment diagram is complete. Each value can be found pretty easily if you think in terms of increments and areas. I recommend pausing here and working it through for yourself. If we need to, we can always get the exact functions for shear force and bending moment under a given load by integration. Integrate the distributed load to get the shear force function. Then use the points you already know to determine the integration constant. Do the same again for the bending moment. Integrate the shear force. Then use the known points to determine the constant. Of course, the usual method of cutting the section and using equilibrium equations to calculate the internal forces is based on exactly the same core idea. You are still just splitting the beam into two elements and looking at the interaction between them. But inside that calculation frame, the physical process of how internal forces are created and transmitted is hard to see. And when the loading gets complicated like this, the calculation itself becomes pretty cumbersome. But now, instead of relying on calculation, we can draw the shear force and bending moment diagrams quickly from the equilibrium and transmission mechanism together with the area and increment relationship. So I hope you no longer get distracted by upward or downward, clockwise or counterclockwise, positive or negative. Those are only part of the calculation framework. What truly matters is not the calculation itself, but the physical essence behind it. If you would like more practice, I have also included my practice handbook in the description. It contains 30 carefully designed examples to help you master shear force and bending moment diagrams, starting from support reaction calculation and going through the full process step by step. If this video helped, please like and subscribe.